by Chicheng Zhang on efficient active learning of sparse half-spaces.
There's a controller somewhere. Oh, there it is. Yeah, so Chicheng was a visa casualty. All right, so this is about active learning. So let's think about classification problems where you have some labeled examples. You want to find a prediction rule. But we're thinking about a situation where you have a very large amount of unlabeled data, and then it costs money to get the labels. So your goal is to minimize the number of labels required in order to learn effectively. All right, so in active learning, what happens is we're interactively choosing which examples to label as the learning algorithm progresses along in the process. Right, so this particular paper is about attribute efficient active learning. So we're thinking about situations where the correct predictor, the correct classifier, only depends upon a small number of attributes, or a small number of features. So it might look like sine of 3.4 x3 minus 6 x87 plus 7.32 x101. Okay, so we're thinking about a situation where we have a labeled distribution D, an unlabeled distribution D sub x, and we're going to have a restriction. The restriction is that D sub x is an isotropic log concave distribution. Then we're going to add a sparsity assumption. We're assuming that the truth is S sparse with some amount of adversarial noise. And S is, you should think of as being much, much smaller than D. Okay, so now we're trying to do essentially PAC learning. So you have the ability to draw unlabeled samples from D sub x, and then you can ask a query oracle for the label of any chosen x. Then your goal is to efficiently learn the vector W that has an angle at most epsilon. So we're thinking about half spaces. So then, without any sparsity assumptions, the number of label queries required is known to be D log 1 over epsilon. It's a paper that we worked on a while ago. Okay, so there's two pieces of prior work which are very relevant. One of them is if you're doing membership queries, which means you have the ability to manufacture your unlabeled examples, then there's an efficient algorithm which uses S and then polylog D and 1 over epsilon. Okay, but the ability to synthesize your examples creates, in practice, relatively unnatural examples, which means it's a difficult algorithm to actually apply in many situations. So instead, you would like to have an algorithm which only uses natural examples, which are coming from the distribution D. And there's this kind of two results. One of them is that you can have an inefficient algorithm that uses S polylog D 1 over epsilon labels. Or you can have an efficient algorithm which is S over epsilon squared labels. So this leads to the question, can we get an efficient PAC algorithm that uses S polylog D 1 over epsilon labels? Right? So it's a very natural question given the things that have come before. And the answer ends up being yes, you can do it. There's an efficient PAC active learning algorithm, which I'll go through in a moment, that tolerates some amount of adversarial noise and has an O of S polylog D 1 over epsilon label complexity. There's a slight variation for bounded noise, which is more noise but less adversarial. Okay, so I'll give you the algorithm outline. It's actually a pretty simple algorithm. So the structure is when we're going to have a bunch of phases. We're going to have log of 1 over epsilon different phases. In each phase, we'll draw some samples conditioned on the weight vector from the previous phase dot feature vector being very close to 0, where the closeness is given exponentially by the phase. And then we have a refinement step. So it's just going to iterate over and over again. And now the question is, what happens in the refinement step? Okay, so when we refine, we're going to be thinking about hinge loss minimization. So we're going to find the V, which minimizes the hinge loss with respect to the data set for the kth phase, subject to two constraints. So you have an L2 constraint, which is exponential on the phase, and you have an L1 constraint, which is exponential on the phase. So the combination of these two constraints is kind of where the magic happens. And then after you find this V, you might in general have a vector which has a large number of non-zeros, so you just impose a hard threshold which preserves the largest S magnitude parameters. So that's it. Are there any questions? Yeah. If my name was actually Chicheng, yes. But as it is, I think you want to look at the paper.
Other questions?
All right.
Okay.
End conference.
Let's thank Sean again.
All right, so this was the last talk of Cult. It's not the last session. We still have a poster session with a lunch, which is everything's going to be served right here. I wanted, on the behalf of the scientific committee, to thank you all for coming. You make Cult. I think it's a great, it's not just great talks, but it's a great community. It's been great to see all of you here. Thank you very much. One last time, I'd like to thank our sponsors that make this happen. So the silver sponsor are Amazon Web Services, the Shaw, IBM Research, Mobileye. The gold sponsors are Baidu, Microsoft, and Apple. And the platinum sponsors are American Express, Google AI, and Western Digital. So thank you, everyone, and we'll see, hopefully, all of you next year in Phoenix.